let's see if we can maybe summarize what we've learned so far about measuring and measurement instruments. Um, to begin with, both the graduated cylinders and rulers are these things called graduated instruments because they have some lines. And so what I want to just take a few notes on quick is determining the scale of a graduated, it's called a graduated instrument. And so a graduated instrument is anything that has lines and numbers on it that we use to make a measurement. So, and so once again, the scale, or what I'm calling the scale, is how we count up by all of the little lines in between the numbers so we can make a proper measurement and then that last estimated decimal point. So the first thing we need to do is subtract the difference. Oh gosh, that's kind of redundant. Difference means subtract. So if you want to rewrite this in a way that makes more sense, that would be fine. Maybe we should say find the difference between two adjacent values on the instrument. So this instrument could be a ruler, could be a graduated cylinder. Adjacent means next to. So it's just two numbers that are right next to each other that are written. And once again, the scale should be the same all the way across the instrument, so it doesn't really matter which two you choose. So you're gonna find that difference. You're going to subtract those values. And then what you're going to do is divide the difference by the number of spaces between two adjacent values. And that's it. That's our two steps. Right? So you find the difference between two adjacent values on this instrument, whatever it is, ruler, graduated cylinder, whatever that the thing happens to be. Burettes, we had talked about those. We might possibly use those. They have the same kind of scale. Beakers have these too, but once again, we're not going to use beakers to measure just because they're, and flasks also, but they're not really accurate enough to do this sort of thing with. But it's always the same process. You subtract the values, and two that are right next to each other, and you divide that difference by the number of spaces, and that will always give you the scale. Okay, we've done several examples of that between the ruler and the graduated cylinder, so I don't think we need any other examples of that at the moment. What we do have to do, though, is maybe just practice this a little bit. So I've got some examples that you're going to put in your notes on page number 8. Okay. So they're going to look like this. I'm going to have those handed out to you in just a moment, and if you need to pause the video to do that, that would be fine. All right. So these are examples. I would probably just put them sideways on page 8. If you want to maybe cut them, that might even be better. Yeah, you probably need to cut them and put them in the top half of the page because we're gonna do some other examples of some things in the bottom half of the page, possibly here. So there we go. That's what our examples look like. So I'm going to kind of zoom into these. We've got some graduated cylinders and some numbers. So we're going to take a look at doing all of these and seeing what happens with them. So on this very first one, there we go. I'm kind of zoom in a little bit. Once again, these all have these meniscuses. They're curved shapes, even maybe a little bit better than the examples, the live examples that we did a couple of minutes ago. So we're going from 2 to 3. Right? So the difference there is 1. Those are two adjacent values right next to each other. Once again, count all the spaces. Usually there's 10 spaces. So the scale is 0.1. And to do this to begin with, it might even be helpful just to kind of write the scale off to the side. So then we're going to start counting. 2, 2.1, 2.3, 2.5, 2.6, 2.7, 2.8, 2.9, and then 3. So this value is between 2.9 and 3. So we know once again that tenths decimal, because we can measure to the nearest tenth. So we need one more decimal place. So my best value for this might be 2.95 milliliters. That would be my measurement on that graduated cylinder. I'm going to do one more, and then you can work on some of these on your own. Oh, let's just do the next one over. I kind of move and scroll things a little bit here. Maybe zoom in just a little bit more for this one. All right. So I hope your copies look as kind of clear as mine do, but we're going from 10 to 20. Subtract those, we get 10. There's also 10 spaces. 10 divided by 10 is 1, so we're counting by 1s. So it's 11, 12, 13, 14, 15. So we're between 14 and 15, and those are whole numbers. So once again, it looks like we're about halfway in between there. So my best answer for this would probably be 14.5 milliliters. Now, where you put your answers on this, I don't really care. I would just write them somewhere in the neighborhood. So as we go back and review this, you have those examples. I'm going to leave the rest of these on your own. I will write some the answers to this for Mr. Van Dyke, so he can go through them with you. But yeah, I just want you to take a minute or two at your table, and if you need to pause the video at this point to do that, that would be great. Take a couple of minutes, see if you can come up with your best answer for these last three, and then you can kind of go over those as a class. Now, looking at the measurements of the lines, a lot of this depends upon your ruler. Right? We could measure this with the centimeter side of the ruler, right? And doing that, we could get that to the nearest tenth of a centimeter, right? Because these lines are just one, and there isn't. I mean, and there's just one in between, so it's just 1 centimeter. So if we did that, we might estimate this to be like 3.7 centimeters. But if we use the other side, right, our scale here is from one number to the next is 1, and there's 10 little spaces. So this already, each of the little spaces, each of the little lines is to the nearest tenth. So we can estimate one more. We can estimate to the nearest hundredth of a centimeter. So we might want to do that. Now, the hard part about my ruler, and that happens with some of these at the tables, is the edge is kind of worn off, so I can't really tell exactly where that end should go. I'm going to estimate, because this is going to be kind of an estimate, about right there. And by the way, you'll find out I get kind of grumpy when you start beating on the table with the rulers. Some of you think you're percussionists or something. And this is why, because then we can't use the rulers as effectively when we go to measure things. So now if I come over here on this end, this is where I'm going to read it. And I can maybe zoom in a little bit more. We need to be able to read the numbers too. So let's try this. There we go. This is between 3 and 4. This number right here is the 3. This number over here is the 4. So if we're counting from the 3, and we're counted by points, point ones, 3.1, 2, 3, 4, 5, 3.6, 3.7. This is actually 3.8. Is that right on 3.8? Gosh, that's pretty close to being right on 3.8. So if it's exactly on 3.8, we would write 3.80 centimeters. Because once again, we need to be estimating that one more decimal place. Now, if you said 3.79, or 3.78, because you think it's a little less than that, that would be fine. Once again, these rulers are sometimes off just a little bit. Once again, depending upon how the edge might be kind of beat up or something. So just give it your best, shot, and we'll kind of go from there. But for my ruler, with my measurement, looks like about 3.8. Tell you what, I'm going to do one more of these. I'm going to do kind of the line off to the side here, and then I'll let you try the other couple with your classmates again, with who's at your table, and we'll see what you can come up with. So I'm going to line up the left end as best I can. I'm just going to zoom in on the right side of this. So let me slide it over a little bit. There we go. So for me, it looks like 5.4, but this one is not 5.5. So I'm going to put 5.47, sure. Looks like 5.47 centimeters to me. So you can go ahead and take a look at the other ones of these with your classmates. We've got 2 more of them. See if you can come up with what you think those measurements might be, and then you can kind of discuss them as a class and see what you can come up with for overall measurements. Okay, so that should go on the top of page number 8. Our last little topic is going to be a couple of numbers that get thrown around a lot in measurement. And those are the numbers, those are the words accuracy and precision. And they do mean different things. They also kind of mean slightly different things depending upon if we're looking at a single measurement or an entire group of measurements. We'll find out the one thing in chemistry and physics, other sciences, is if we do an experiment, they have to be repeatable. I mean, if I do an exact experiment and I end up with a result, anyone else should be able to set up the equipment the same way I did. If it's a good experiment and kind of a valid conclusion I'm going to come to, somebody else should be able to set up exactly the same equipment, exactly the same way, and get pretty much exactly the same answer. So, accuracy and precision have a lot to do with that. So if we have 12 people taking measurements, right, all 12 people should come up with about the same answers, and accuracy and precision might mean something different for all 12 of those measurements as opposed to just a single one. So let's talk about this for just a couple of minutes, and we'll see what I mean by that. So let's take a look at accuracy first. Accuracy is really going to measure how close in a result you get, how close of a measurement that you take compared to its actual value. I mean, when we were measuring those lines of the graduated cylinders before, there is an actual value there. And so accuracy measures how close are you to that actual, or sometimes we say accepted value. So we'll just say, it's not very scientific kind of speech, but it's how close a measurement. So that's just one. I'll say, or an average of many measurements is to the actual value. So accuracy is how close a measurement, a single measurement, or an average of many measurements is to the actual value. So if I want to measure something and its actual value is 21.5 centimeters, right? Accuracy of a single measurement might say, how close am I to that measurement, the 21.5 centimeters? On the other hand, I might take 5 or 6 or 7 measurements, and what I would do is I would take the average of those, and in that case, accuracy would tell me, how close is that average number to the 21.5 centimeters. So we'll do some examples of accuracy here in just a moment. Precision, on the other hand, precision for a single measurement tells me really how many significant figures there are. 21.67 centimeters is more precise than 22 centimeters. The more significant figures you have, the more precise the number is. So precision, I might write down 2 separate definitions because it depends upon a little bit, more specifically, do you have just one measurement or do you have many? Accuracy, it's basically the same definition. It's either you have a single measurement or you have an average. How close is it to an actual value? For precision, let's just do it this way. For a single value, it is the number of significant figures. So I said 21.325 is more precise than 31. So there you go. Now precision, on the other hand, with many measurements, precision is how close are they all to each other. And so we'll do some examples of that in just a minute. So as I said, I think earlier, when I do these notes, generally I tend to underline. I kind of missed one here. Underline main headings. And then sometimes there's numbered or bulleted lists. Here's kind of a main heading. Here's some definitions. Yeah, so if I have two kind of definitions or two kind of set points, I do generally do bulleted lists. My bullets, though, are more like hyphens. Sorry, my computer tried falling asleep. So the second hyphen is kind of a second definition for this precision. So this is for a set of values, precision, shows how close the values are to each other. So they do mean different things. You can be accurate and not precise. You can be precise and not accurate. We are striving for both. We are striving for every measurement that you take to be accurate and precise. You want it to be as close as to the real measurement that's actually there as possible, and we want you to have as many sig figs as possible. Right? And if you take a whole set of measurements, right, we want all of these measurements to be very close to each other, and we want the average of all of those to be very, very close to what the actual value is. But let me give you some examples of just either some single numbers and some individual and some groups of numbers that are maybe accurate and precise and so on and so forth. So let me go back to flip this over to page 8. We've got our measurement numbers on the top, the ones we did in class, or the ones I did with you anyhow. You'll be filling in the other ones in class. So let's break this into a couple parts. Let's talk about single measurements. And then over here we might say many measurements. Now, many kind of depends upon what we're doing. Sometimes we only have time for 2 measurements. Sometimes we have time for 10 or 12. So many is anywhere in between. Many is more than 1. So let's just say actual value. Let's say we're trying to measure some amount of liquid. The actual value that is really in there, and I know that from some sort of thing that I've done, is 21.9 milliliters. Let's say you've done one value that is 21.903. So what do you think? Let's just look at accuracy first. Is this value close to this one? Yeah, I'd say. Right, it's only off by 0.003 of a milliliter. Absolutely. So this is a very accurate number. Is it precise though? Precise tells me how many significant figures there are. Well, if we look at our significant figure rules, there's 1, 2, 3, 4, 5. Yes. So this thing is accurate and precise, both. Shows a high level of accuracy. It's very close to the number it's supposed to be, and it is also precise. Let me do another one. Let's say somebody else happens to measure this, and they get the number of 23.6517 milliliters. They're measuring exactly the same thing, and this is the result that they get. So the first question is this accurate? Is this really close to the number it's supposed to be? Not so much, right? They're off by 2 milliliters. But is it precise? Absolutely. You know, if their measuring instrument gave them 1, 2, 3, 4, 5, 6 sig figs, that's huge in chemistry. There aren't very many measurements we can take that are 6 sig figs. So this thing would be an example of something that is not accurate, but it is precise. Lots of sig figs, but it's not really at all close to what it's supposed to be. Let's see if I can go one the other way. Let's say somebody else measures this thing, single measurement, and gets 22. Is it accurate? That's pretty close. Off by 1/10 of a milliliter. for our precision, or for our, excuse me, our accuracy in here, now I'm using the wrong word. For our accuracy in here, that's not too bad. Is it precise though? Well, you've only got 2 sig figs. This person measured it to 5, this person measured it to 6. You've only got 2. So this one, I would say accurate. Yep, it is accurate. Maybe not so precise. It's kind of precise. 2 sig figs is not all that bad, but most measurement instruments in here, you should be able to get 3 and sometimes 4 sig figs. So measuring to just 2 is probably not the best thing to do. That means that if this is the most precision you can get out of your measuring instrument, your graduated cylinder, I would probably pick a different graduated cylinder that would somehow give me more sig figs, so I can be a little more precise with that measurement. And finally, let's say one more person measured this, and they got a value of 28. Gosh, that's not even close. It's not accurate. And gosh, we only have 2 sig figs. That's not very precise either. So this one is not accurate or precise. Both of them are just pretty bad. So out of all of these, which do we really expect in chemistry? Well, we'd like the top one. We'd like you to be as accurate and precise as possible. And one we really, really can determine, and that's more the precision. Right? The precision you can absolutely determine by choosing the correct piece of equipment to measure something with. Like we're going back to the ruler and that ruler example. We do not want to use the straight up centimeter side of the ruler, because if we use the other side, which is labeled the millimeters, we can get 1 more sig fig out of that. So you always want to choose your measurement instrument to give precision as much as possible. Accuracy is then what's up to you. Right? That determines how you read the thing, how carefully you're actually reading what's going on. Things like rulers and graduated cylinders, are you looking exactly straight at them? Are you tipping them somewhat? For a ruler, do you have the 0 on this end exactly at the end of what you're trying to measure? All of that goes into the accuracy. Precision is just built into the scale. That comes from the scale of the instrument. Accuracy is kind of on you in terms of how careful you are. Let's do a couple of example quick with many measurements. For this one, I'd rather use maybe just a visual rather than numbers, because I think it's easier to see. Most of you have probably seen a bullseye before, correct? So let's just say you're shooting for a bullseye. I'm just going to draw 2 of the circles, and you're trying to hit the middle. Right? The middle is what you're trying to get. This looks more like a donut than a bullseye, but I think you get the idea. In the interest of time, there'd be a lot of rings around here. I just want to draw the one in the middle. So you're going to shoot 5 arrows at it. If you have accuracy and precision, all 5 of those arrows, so accuracy means is it close to the middle, right? That's what you're trying to hit. Accuracy and precise means they'd all be right in the middle. Right? Because for many measurements, accuracy still is the average of all of those. Is the average of all of those in the middle? Absolutely, the average hit is right in the middle. Precise is how close are they to each other. Right? And these arrows are physically very close to each other. So this one is both accurate and precise both. If you are, I guess, in professional bow and arrowing, or maybe this could be darts, right? If you play professional darts, you're trying to get accuracy and precision both. Accuracy and precise. Accurate and precise both. This case, the arrows are all over there. Oh, I drew 6. I'm sorry, so I was supposed to draw 5. So the first of all, are these accurate? Well, accuracy means on the average, these things are all in the middle. Not so much. Precise is they're all real close to each other. Yeah, they are. They are real close to each other, but they're not where they're supposed to be. So these are still precise because they're very close to each other, but they are not accurate. I'm sorry, I'm kind of running out of room on the edge of my notebook here. These, let's try it. Let's say one over here, one over here, one over here, one down there, and one there. Now, on the average, if we just kind of average all these out, they actually are kind of in the middle. I mean, if it's one on the left, one on the right, you kind of average those, you get in the middle, right? We have 2 kind of high, 1 kind of below. If these things are in a symmetric pattern around the outside, on the average, they still end up in the middle. So this actually is accurate. Seems kind of weird. But on the average, they're kind of in the middle. On precision, though, not so much. Precise means they'd be very close to each other. These are definitely not precise. Now my last example, I might do something like that. On the average, are these things in the middle? Well, no, they're all on the right. On the average, they're over on the right side somewhere, so they're not accurate. They're also not very close to each other, so these are not precise. So these are not accurate, and they're also not precise. Okay, so that's a review of just some basic measurement stuff. You are going to have some practice with this. We've got a practice worksheet that we'll do. It's got some graduated cylinders on it. It's got some rulers on it. Some of the graduated cylinders actually have the rounded meniscus. Some of the graduated cylinders are more flat across the bottom. If it is flat across the bottom, you can just kind of read straight across. Otherwise, read the bottom of the meniscus and come up with your best answers. Have fun.